classical random walk subject to stochastic resetting. This topic has been slightly touched upon by Edgar, so I'll continue with that. Well, I'll describe the general framework of stochastic resetting, and so this has been an ongoing work. So for today I'll talk mostly about the work that has been done with Apurva Nagar. He was senior to me in TIFR, doing PhD with Mustanse Verma. Edgar Roldan, well, much of the analytical stuff that I'll talk about has been done with Edgar, and also probably I will not have time to talk about the work that I did with Luca, but Luca is here, so you can catch him. Okay, so let's start with what is the general framework that we are interested in. So this is some real data of stock price. At least some of you would be interested in it, if not all. So here this is stock price plotted as a function of time. Okay, time here means these are the days. 7th of January, well, this is January, and so this is 7th of January, 8th, 9th, and so on. And these are the stock prices that have been plotted as a function of different days in January 1987, and you see that there are small fluctuations here and there, right? The stock prices are fluctuating on the scale of a few days, but then you see that suddenly there is a big crash, like there is a huge fall in stock prices over a very short interval of time, that is over the same time scale over which you see the fluctuations here. Over that same time scale you see a huge fluctuation, like a big drop in the stock price. Okay, and that came to be known as Black Monday. It was a Monday on which this thing happened, and so the thing to note from this one is that you have the same time scale over which most of the time you have small fluctuations, but once in a while at a random instant, you don't know when it would, maybe the stockbrokers knew when it would happen, but at least the common people did not know when it would happen. And when it happened, there was a huge fall in stock prices over a short interval of time. Qualitatively similar data, similar thing can be observed in what came to be known as Black Plague. So here what I have plotted is the population, millions of people, the population of medieval England as a function of, well, here you don't see population fluctuating much over the scale of a day. So here you have to look at years, several years and so on. And what you see is that there are small fluctuations, like over the span of a few years, people die, people are born, and so on. But then, there was this epidemic that happened between 1348 and 1351. And in that epidemic, the population was halved. So half the population died. So you see a huge reduction. That's a huge reduction as compared to the small fluctuations that you observe here and there. There was a huge reduction in population size over a short interval of time. So the time scale is not changing. It's the same time scale over which you are making the observation that once you see small fluctuations, and that's more often than those instances where there are huge fluctuations, and this is one instance. So that's the general framework that we are interested in. So the basic features of the two data that I just showed, and you can see many other examples, and this cleavage, this recovery that Edgar talked about, that also had this feature embedded in it. And that's the following, that what are the basic features? That there is an underlying stochastic dynamics. So what do I mean by stochastic dynamics? A dynamics for which the outcome is not certain. It could be this, it could be that. So that's why it's called stochastic. For example, for stock prices, if you buy a stock today, you don't know whether the price will increase or decrease tomorrow. With certain probability it will increase, with certain probability it will decrease, with certain probability it will remain the same. So that's stochastic. So there is an underlying stochastic dynamics, and that dynamics involves two kind of behaviors. So one is there are small or incremental changes over short time intervals, as you saw in the data of the stock prices and the population, that there are small changes and then there are big changes over short time intervals. So these small changes are happening more often than not. So there are these small changes, and then once in a while there is a big change, and then this kind of stuff. Okay, so there are sudden interruptions. So there is an underlying stochastic process that leads to small fluctuations, and then there are sudden interruptions. You don't know when they will happen, but if they happen and when they happen, there is a huge fall, huge reduction in the the population size or the value of the dynamical variable over the same time interval, like over which you see fluctuations everywhere else. Okay, so the question is, suppose you have a dynamics of this sort, that you have small fluctuation, once in a while there is a big fall, and then again you repeat small fluctuations, big fall, small fluctuations, big fall, and you ask, well, I observed the system for a very long time, let's say 10 days, or let's say in the case of population maybe over a century, or so you ask, can one characterize the state of the system at long time? So I observe this system, keep on observing it, and then what is the state of the system? What is going to be like? Like for example, like is it going to be that there aren't what is the value of this dynamical variable at long time, or more precisely, what is the distribution of the dynamical variable? I mean, or what does the state look like at long times? So that's the question that we are going to address, and so there is a saying that says that you should walk before you run. So before you try something very complicated, you should try out something simple, something for which you can compute everything like analytically, and then which gives you a scope to generalize your theory. You have to have some ground level over which. So what was done is that instead of looking at population dynamics or stock price variation, people decided to look at the motion of a simple random walker. So it's just one random walker, okay, a single one. So the random walker is doing what? I mean, what it is supposed to do, namely random walking. And the way it random walks is, we know how it random walks, that it tosses a coin. So at every step it tosses a coin, and if the coin falls on its head, it moves to the right, and if it falls on its tail, it moves to the left. Okay, and that's what it does. Okay, so the fluctuations that you see, so what I'm plotting here is, this is the position of the random walker as a function of time, and the red ones, these are the trajectories. So this red one is the trajectory of the random walker. So once in a while it goes to the right, but then it moves to the left, maybe right, left, etc. Okay, but then what are these big blue big jumps that you see, which are denoted by blue? So these are supposed to represent the large fluctuations that were there in those data of population dynamics and so on. So here what you do is that the random walker is random walking, but once in a while, and you don't know when, let's say at a sudden instant, you decide to bring the random walker from wherever it is, at one go you bring it to its starting position. So it started out from 0, then it random walked for some time, and it went there, and what you decide is that at this time you just bring it at one go from its current position to 0, and then again you repeat. Okay, so these are the times at which the random walker has come back to its initial position, and these times are completely random. I'll show what do I mean by random, or how random it is, or how to characterize it, but it should be evident from this figure that there is no reason for this random walker to not have reset at this instant. Okay, so this is just one realization of the random walker. Okay, if I look at the history of the random walker, this is just one possible trajectory of the random walker. Yeah.
Is the resetting step somehow different from the rest of the random?
Yeah, the resetting step is the following, that for the rest of the motion, what is happening is that in one time step you can go either to the left or to the right. Okay, so these are small fluctuations. In one step you cannot jump from here to there. Okay, while resetting at one go, wherever you are, irrespective of your current location, you make a big jump to your starting position. So in one time step, during resetting, you are allowing the particle to make a huge jump. Okay, well, it may be a small jump, because if you are very close to 0, you make a small jump, but independent of where you are, you come back to your initial location.
Right. But so in the case of the plane, for instance, you are treating that as
Resetting in the population size, that it's not really coming to 0, thankfully not. Okay, so it's not coming to 0, but it's some base level. But well, we can this is just a this is just a model that you set a base level and you say that once in a while you come back. We will see later that this base level where you come back to reset, it doesn't have to be one value. You can choose it from a distribution. Like it may come back to random values. Okay, but set of different values. But the more important thing to realize about this process is that over the same time interval, you have two options. Either you make small fluctuations, you just fluctuate around your current location, or you make big jumps to somewhere. Okay, in this example, that somewhere happens to be the initial location, but we will see later that you can generalize it. It's not so.
But even completely stochastically, you may have big jumps occasionally. So
No, you cannot have, by random walking, you cannot make big jumps. Because random walker by definition it is allowed to move either to the left or to the right. You cannot go from here, you make a, so then your step size is basically what is allowed by your normal dynamics. You cannot make suddenly.
I think what is maybe this is one definition of random, just one plus minus, but you can take a distribution which is exponentially distributed.
Yeah.
So each jump step is exponentially.
I am not
In that case, accidentally once a while, it will
Yeah, you may come back to it.
come back to 0. But that measure is 0. So if you wait sufficiently, has thing happening in time 0.
Unless you take a probability distribution which has a power law and so on. So this is much simpler.
This is simpler. This is a finite, for a given time, that's finite density.
Absolutely. Okay, so here actually it's a delta function, like two delta function. Okay, so either you move to the left by 1 unit or right by 1 unit, not like 10 units to the left and 10. Okay, so for the students, I think you can disregard, or you can I mean, I'm not asking you to completely disregard, but it's important that you understand the basic model. Okay, so the basic model is very simple, that you random walk, you go left, right, and once in a while you go from here. Let's say you make a big jump and you go to Belur Mutt. Okay, that is also allowed. Like I somehow happen to have some ability to make a big jump to Belur Mutt, and so that will be a resetting. Okay, and here it's why it is called resetting, because you are coming back to your initial location. That's why it is a reset. You do reset. I'll tell you one example of a reset that we often do. That let's say I want to search something on Google. Okay, so I type something. Let's say random walk. Okay. Then I get a link on random walk, but then I went to that link and then there I found something about Robert Brown. I click on that and we start talking about England and then May and then election and so on. And at some point say, oh no. My initial aim was to find some information about random walk, and now I am getting interested in Brexit. So that's not what I want to do. So what you do is that you make a big jump in the Google. So what you do is that you come back to your first page and you don't click on Brown and so on. You say no. I'll stick to what I wanted to find out about. So that kind of thing.
Shamik?
Tell me. Okay, I can see. Tell me.
There's another example in the computer that you reset the computer and you start from 0 when something is not working.
Oh yes. Yeah, that's the brute force method, right? There is something is not working, you restart. Okay, you call it restart. Yeah, exactly. Yes. So something is not working, so you restart. So this is one realization of the random walk. And if I change the realization, like obviously everything changes. Here also there are big jumps and there are small jumps. But the difference between the previous one and this one is that, the previous one and this one is that, the time at which it resets is different between the two realization, and of course the trajectories are also different. So I may think of the gap, the time between successive reset to be a random variable. It's not one fixed number. It may have many different values, and therefore something that has many possibilities is a random variable. That's the definition of random. So I call inter reset time tau which is which is shown here. Tau is the time between two successive resets or two consecutive resets. That's tau, that's the inter-reset time, that's a random variable. Okay. Now, let us first look at the situation when there is no resetting and the guy is the random walker is just doing plain simple random walk. Okay. And if you go to continuous space and continuous time, then it becomes Brownian motion, but basically the features are more or less the same. So, what you have is, you have just a random walk who is random walking. So, this is for simplicity, I have taken a one dimensional random walk, but much of the results can be generalized to 2, 3, 26 and infinity. So, these are the only limits that I somehow have been taught about. I do not know. So, 1, 2, 3 infinity. Do you know about this book? George Gamow. Okay. Anyway, so this is a random walker who is moving on one dimension and there are no boundaries. Okay. So, it can go as far as it wants to the left and to the right. And then what we know is that suppose you start with a delta function at x equal to 0. That is, you start with the random walker on location x equal to 0 at time t equal to 0 and you ask, what is the probability distribution of the random walker? What is the probability of finding so suppose this is your x equal to 0. So, you start with a delta function, that means the random walker is surely at this location at t equal to 0 and you ask, I let the random walker do random walking and then after some time, what is the probability that it is here, what is the probability that it is there and there and there and so on. Okay? And that is a well known result, that is a you get a Gaussian distribution. Okay? So, you have a Gaussian distribution. So, this is a Gaussian distribution at t equal to 10. You started out at x equal to 0, still most likely you are at x equal to 0, but there are smaller probabilities of finding the particle away from your initial location, and the longer you wait, the particle spreads. The longer you wait, what is going to happen is that the particle is going to get further and further away from your initial location, and that is what it is happening, that the probability distribution is getting broader and broader, and of course it has to come down. The peak has to come down. Can somebody tell me why? The student? Total, yeah, because the whole thing is normalized to 1. So, if it spreads this way, then it better shrinks in the other direction. Okay. So, at long times, if you have some space, you say that it's going to be flat, for example. If you wait for an infinite amount of time, so you say that the particle is going to be anywhere at long times. It has equal probability of being everywhere in the allowed space, let us say. Okay. So, you have unbounded fluctuations. Fluctuations are unbounded. There is a mean location. The mean location is where you started out from. The mean is at x equal to 0, but the fluctuations are unbounded. Okay. So, that is to say, one puts it differently. One says that, if you look at the mean square deviation, this is proportional to t. The longer you wait, it is going to increase further with time. So, you have unbounded fluctuations. Now, the question is, what happens, this is pure plain and simple random walk. What happens if I include resetting in this scenario? Let us see the effects in the simplest setting, namely the setting of the random walk, this one. So, what is going to happen is, first I have to tell you, I told you that you do not know when the random walker is going to reset. So, that is a random variable, the time between successive resets, okay? That is a random variable. So, you can do an experiment for a given system, you can draw the histogram, that is how you get the distribution of the random walk. And suppose I tell you, I give you that this distribution is an exponential. Okay? So, it is an exponential with this form, rho tau equal to r exponential minus r tau. And when you have an exponential distribution, the first thing that comes to your mind is, oh, exponential means there is a factor r, and what is that r? 1 over that factor r is the average time between resets. Okay? Because the resetting may happen after 1 minute or after 5 minutes or after 7 minutes or after 20 hours maybe, and I take the average of all this, and since the underlying distribution is an exponential, you get this average to be 1 over r. So, of course, if you have resetting compared to the bare model, the first thing that you would expect is, well, when there was no resetting, there was nothing, no boundaries, nothing were there. So, there was nothing that could stop the particle from going very far from its initial location. It started out from here and then it did and after some time it just went this way. But here when you have resetting, you might think that, well, it may not be so easy for the particle to go very far, because, well, you try to go very far, you try to go very far, but then the resetting is there. So, you make this and then you do this, but then now I have to really, okay, I try this. So, you reset. Okay. So, you say that the particle cannot go very far even at long times. It does not matter how long you wait, but because resetting is there, it is not that you wait for 500 years, there will not be any resetting, it is always there. Resetting is there, so then you would think that if you have resetting, the particle cannot go very far. So, what might happen is that the fact that you had a probability distribution for the random walker that was spreading as a function of time, it might get stopped, because what was this spreading telling you? This was telling you that the longer I wait, this is going to be broader and broader, and there will be higher probability of finding the particle at very far away location. This thing was increasing, this thing was getting fatter. But now you might think that such a spreading, such an infinite spreading, the fact that you have a finite probability of finding the particle very far away from your initial location, and the fact that this finite probability kept on increasing the longer you wait, would not be there if you have resetting. And what you might expect is that it may so happen that this distribution, the fact that this distribution kept on changing as a function of time, gets stopped. I mean, it simply does not happen. What happens is that you wait long enough and you converge to a distribution that does not change any further with time. And you would call such a state, from common sense, you would say that the system has reached a steady state. Steady state means what? This is the definition of a steady state, a state for which the probability distribution does not change as a function of time. And indeed, it has been shown for this very simple model that what I am plotting here is, so what is the probability that I am at location x at time t, given that I was at x0 at time 0, x0 could be 0. So, x0 is your initial location, this is your initial time, given that I was at x0 at time 0, what is the probability that I am at x at time t? This is the quantity that had that Gaussian shape, and if you incorporate resetting, it has been shown, it is consistent with our physical understanding of the whole situation, that this distribution, it gets to a time independent form if you wait long enough, and this is the form of the time independent distribution. So, instead of looking at the formula, let us look at the figure. So, what it tells you is that, you see, this is p x of t x0 0. What is the probability that I am x at time t? Given that I was at x0 at time 0, I had waited long enough, this distribution becomes an exponential. Okay? Still, you are more likely to be found at where you had started out from, but then you have exponential tails. And what does an exponential tail signify? It tells you that beyond a certain distance, there is negligible probability of finding the walker. Okay? That is what exponential means, right? You know this, right? You must have done it in RC circuit, and there is an inherent time scale. So, here there is an inherent spatial scale beyond which the particle will never be able to get to, like there will be very small probability of going very far away from your initial location. So, if you have an exponential distribution, then at once you see that the fluctuations get bounded. Fluctuations get bounded because how could you have infinite fluctuations? Only if you had allowed the particle to go further and further away from, you are allowing the particle to go very far away from your initial location, but the resetting is bringing it back more often than not, and therefore you have such an exponential distribution. The interesting thing is that here you have been able to bound the particle to a particular spatial region. you have said that the particle is going to remain more or less within this region, and you have been able to achieve it without imposing any physical boundaries. So, come to think of it, it might
But the statement you are making would be true even if it is an exponential with a fixed sigma.
this is an exponential with a fixed. Huh?
Gaussian, fixed.
Gaussian, the rho tau meaning?
Gaussian with some fixed sigma.
Rho tau meaning, for the rho tau.
Tau can be
No, it's like an e to the minus x minus x.
Yeah, of course. So, we will see, no, the significance at the moment you do not quite see what is so significant about exponential. So, what we will see later is that it all matters whether the first and the second moment of the underlying distribution are finite or not. So, this is just an example to show what resetting can bring in. Later we will generalize it and see what new things or what general statement can one make about this reset.
So, just P steady state x px,
Huh.
it's just px tau, rho tau, integral tau, that's all?
No.
Okay, no, this is too complicated.
Achha. No, this is more complicated. I will come to that probably, because if I get to that, then I will not have. So, at least the physical effect should be clear, right, that you are unable to get very far from your initial location. You have been able to say that the particle is bounded within a particular spatial region, but then this you have been able to achieve without imposing any boundary condition. It is not that you have put some boundaries, and of course, if you put some boundaries, then obviously the particle is going to live within those boundaries, but that is not what so you have been able to dynamically modify its equation of motion dynamics in such a way that the particle has chosen to remain bounded to a confined to a spatial particular bounded spatial region. And it turns out that this is for expert, I will not get into that. It turns out that the steady state that you get to, this one, is a non-equilibrium steady state. It cannot be described by equilibrium laws, and it turns out that this is really the simplest steady state that one can think of, that is out of equilibrium. I will not get to that. If someone is interested, you can catch me after the talk. So, now the question is coming back to like Aditya's question, one basic thing that will show up later, and it will hopefully be clarified by this discussion on power law. See, you have a distribution for the time between two successive reset, and if you have a distribution, the first thing that you ask is, can I define a mean, the first moment of the distribution. Then the second thing that you ask is, can I define the second moment of the distribution, okay. And one broad class of distributions that you can think of is a power law distribution, okay. So, that is a power law as opposed to an exponential distribution. This is a power law distribution. So, what is a power law distribution? Well, still tau is the time between two successive reset, and tau 0 is some time scale, okay. If you have a power law, then you have to have a time scale, and there is an exponent which is alpha, that is telling you how fast the power law is decaying as a function of time. Okay, if alpha is very large, then it is decaying very fast. If alpha is very small, it shows a very slow decay in time. And as we will see later, or probably you can do it in your head, that if alpha is, okay, first of all, alpha has to be larger than 0, because if alpha is negative, then this equation, then this distribution is not positive. Okay, this is a probability distribution. It better be greater than equal to 0. Now, what you can check, just by looking at this expression and doing this integral in head, that the first moment of the distribution, which is rho tau times tau d tau, integral tau 0 to infinity, okay, tau 0, because tau cannot be smaller than tau 0, okay. If you do this integral of, the computing the first moment, you can see that the first moment is finite only if alpha is larger than 1. Second moment is still infinite. To make the second moment finite, you have to have alpha larger than 2. Okay. So, just keep this in mind, even if you do not, it is a simple integral that you can do, but we will see implications of those, and that will so relate to your question. So, the question is, how different is power law reset? See, I discussed about exponential reset, where you were resetting after an exponentially distributed time, And I told you that an exponential distribution has a finite first moment and a finite second moment, and there is a characteristic mean time of resetting, mean time after which you reset. And you ask how different is power law reset, and you may think that, well, it's all the same, because after all you are not allowing the random walker to go very far, so that's still there. It just happens to be that tau is now a power law distributed random variable, and earlier I had considered an exponential distributed random variable, so things will more or less be the same. But it turns out that things are very, very different. In fact, not just very, but very, very, very. I mean, you can add as many very as you want. So what you get is, so this is just a cartoon of the possible scenarios that that may like emerge in this situation. So here, depending on the value of alpha, it is not always certain that you will go to a stationary distribution. It is not always clear, or it is not always the case that although you have resetting, you have been able to confine the particle to a particular spatial region. Like even when there is resetting, it may so happen that you have a probability distribution that still keeps on spreading, keeps on widening as a function of time. Although you have resetting, yet there is a finite probability of finding the particle very far away from its initial location, although there is resetting. Okay? So this may happen if alpha is smaller than some value. I will come to that which value. It turns out that that value is 1. Okay, if alpha is smaller than 1, you may have that scenario, while if alpha is larger than 1, for example this one, then you really converge to a time independent steady state. As you can see, for different distributions I have plotted the distribution, and you do not see red and green. So that means they have been completely masked. That means you have a distribution that is really falling on top of each other. Okay? So if alpha is larger than 1, I will show you how and why. But that is the thing that happens, that for exponential resetting, it is guaranteed that you will be able to confine your particle to, I am sorry, it is for exponential resetting, it is guaranteed that you will be able to confine the particle to a given spatial region, while for a power law, it is not guaranteed. You may, you may not. Okay? And I will come to when you may and when you may not.
So for this row, it is not possible to do any of this analytically. So you have to do it
No. You can, okay, good question. Everything is analytic and exact here. I haven't done any numerical simulation. These are, so that's why I should have, okay, dots. I should have made them with lines. But these are like everything is analytic. There is no numerical simulation. Well, we did numerical simulation to test something, but when we were doing numerical simulation, it was more a test of the numerical method than of the theory. That whether, but anyways, so like everything is analytic here. Okay. So now the question is, for us, let us look at the situation when alpha is larger than 1. Okay. And then I come back to, why alpha equal to 1 is a special point. So let us look at that distribution for a minute. So what is the distribution? The distribution rho of tau, it was going like, if I forget about those prefactors, it was tau to the power 1 plus alpha with a minus sign. And if you do the integral, computing the moment, what you see is that here is your alpha axis. So alpha has to be larger than 0, that is what I said. Here somewhere is alpha 1, here there is 2. And you can just do this integral in your head, and you can see that this is the region where tau is infinite. But as soon as you cross alpha equal to 1, so all these regions, they correspond to tau finite. And what does tau finite imply? It implies that there is indeed a the mean is finite. That is, although you may have fluctuations, but there is indeed an average time after which you are bound to come back to your initial location. While here, what it means is that, well, you may come back, but then the average is infinite. I mean, you may come back, but there are a good number of trajectories for which you do not come back. You come back after infinite time, that is why the mean is infinite, right? That is what it means. While here it means that it is guaranteed that there is a finite average time after which you are bound to come back. And in fact, that is what is shown in this cartoon here. So, what I am doing here is I am plotting the position of the random walker as a function of time, and these black lines that you see, vertical ones, these are the reset events. These are the ones that you reset. These are the time instants that you reset, and indeed you see that there is a finite time. The time is of the order of maybe 2 or 3 units, right? It depends on the value of alpha. So, it is guaranteed that after every of the order of 2 time step you come back to your initial location, and therefore this situation will be closer to what I had observed with the exponential resetting, that tau is finite, and therefore let me just skip this one, let me go to this one. So, that tau is finite, and therefore there is a steady state. The probability to find the particle at a given location x at time t, given that you had started out with x0 at time 0, it goes to a time independent form, and that is the form of the time independent distribution that one can. It is quite remarkable that you can calculate everything analytically. I will probably have some time to talk about the theoretical framework. So, this is the probability distribution that you get, and you can see that this probability distribution has got power law tails. Okay. So, what it means is that if you had exponential resetting, then the probability to find the particle far from your resetting location had an exponential fall. Now you have power law resetting, and you have a probability distribution which is stationary and that has got a power law decay of the spatial profile at long distances. And this turns out to be a generic feature of this resetting dynamics, that whatever input you give at the temporal level is going to show up in the spatial profile for cases in which the dynamics has a steady state. You put exponentially distributed resetting time, you get a distribution which has exponential tails. You give as input power law distributed resetting time, you get a distribution that has got power law tails, as has been shown here. Okay. So, this is a log plot, and you see very nice power law. You can find everything exactly.
Shamik, I have a question.
The distribution is, so it's 2x, 1 over x to alpha minus 1, if I see that.
Yeah. So, alpha has to be larger than 1 here.
And so, but then your distribution is 1 over tau to the 1, so it's slightly, so you don't get.
No, you don't get the same exponent, but the feature remains that whatever you input that you get at the temporal level shows up in the spatial profile. Now, you may ask, well, this I understand hopefully, that when tau is finite, tau average is finite, that is in this zone, then it is guaranteed that after a finite average time the particle is going to come back and I have a steady state distribution. But then somewhere I should see some signature of the fact that although tau average is finite in this whole region, the tau square, the second moment, is like infinite in this region. So, for tau square to be finite, you have to have alpha larger than 2. That should show up somewhere, and that shows up in a very interesting way, and that is the thing that that although when alpha is larger than 1, you have a time independent state, time independent distribution, steady state, yet the second moment has got a time dependence. The second moment is as it is written here, this is the second moment at long times. So, this has a finite value if alpha is larger than 2, while it is diverging if alpha is between 1 and 2. And that is because when alpha is between 1 and 2, although tau average is finite, there are huge fluctuations around it, and that is going to show up in the second moment. So, the second moment is, this may very well happen that you have a power law distribution, it is well normalized, everything is fine, but the second moment is infinite. And that shows up in this nice way, that the second moment is infinite between 1 and 2 at the temporal level, and that shows up as an infinite second moment, at the spatial level. Whatever you given at the temporal level, that shows up in the spatial level. Now let's come back to alpha smaller than 1. So what is so interesting about alpha smaller than 1? Here tau average is infinite. That means it is not guaranteed that there is a finite time after which you are bound to come back. Once in a while you come back after 2 seconds, but for some occasions you might have to wait for 200 years to come back, and then 500 years and maybe 1 billion years. So the mean is infinite. Okay, that's why mean meaning 1 plus 2 plus 1 billion plus 2 billion plus 600 billion, and that's of course infinite. Okay.
Just for alpha less than 1,
Huh.
alpha less than 0 for alpha less than 0.
Alpha less than 1.
Alpha less than
Huh.
1. So in that case we have a similarity for non-reason.
Exactly. So that's why we get a distribution that keeps on broadening. That's right. So here, so this is a typical trajectory of the random walk. You see there are times, there are instances for which the random walker resets almost like immediately. But then there are times for which the random walker just kept on diffusing without showing any signature of resetting. And what does mean tau mean? Mean tau mean you have to average over those instances and this big gap. And this big gap is going to give you a tau average which is infinite. So since here there will be many trajectories for which you don't ever reset within a given time interval, and therefore the probability distribution, it will not show any signature of getting to a steady state. It will just keep on spreading or widening as a function of time, and that's what I have shown here. Although it's at the qualitative level it is similar to the case where you don't have resetting, but definitely there will be some manifestation of resetting, and that shows up in this distribution having a cusp singularity at your initial location. And that, if you are interested, I can tell you that's a clear signature of the fact that the underlying dynamics is out of equilibrium. For a Gaussian distribution, you don't have any cusp singularity. The derivative is everywhere, but here there is a discontinuity at exactly the resetting location. And that's because for experts that happens because, at that resetting location is kind of very special. Okay, maybe it is for all, not just for experts. It's very special because you see, if you think of current, probability current, what are the different ways of getting to that point and coming out of that point? You see that at the resetting location, because of resetting, there is a good chance that you will reset from wherever you are directly to that point. So there is a probability current this way, but there is no probability current that way. You cannot at one go from your resetting location to your current location. You cannot do. You have to slowly diffuse through the intervening space. Okay? So diffusion is always allowed. From here to here there are two paths. One is this diffusion. You go out this way, you come back this way. But then you come back either this way or you come back this way. Cut. So this is what is generating probability current, a source at that x equal to 0 at that resetting location. And whenever you have a probability current, you know that it cannot be an equilibrium, the dynamics cannot be an equilibrium one, it violates detail balance if you know what it is, and therefore it is an out of equilibrium. So let me just quickly tell you something about this exact analytical calculation. So this is something that we developed with Edgar and myself when we were both at Dresden. So it so happened, let me tell you, how at least we got into this. So I was in the 3rd floor and Edgar was in the 2nd floor. I was in one group, Edgar was in another group, and he happened to be present in one of my talks, and he had all this data about transcription and this and that. And so then we started discussing if we can analytically, if you remember in his talk, he showed a model for which he could not analytically solve in full generality the model, he had to do some. So then we thought that maybe there is a way to solve this using, there is a way to analytically solve this model. We could not solve the original model, but we came up with, a zoo of models that can be solved using this path integral technique. And so I'll just describe what it is. So I think this is, I have to show you some slides full of equations just to impress you that I don't do always, maybe okay, forget it. So what is this path integral approach? Actually this gives you a very nice way of, I don't know if as students, some of you have been exposed to Feynman's path integral formalism of quantum mechanics. So there is like before Feynman's work or like around the time of Feynman's work, Mark Katz developed this theory of path integral formulation for stochastic processes, classical systems. There is no quantum mechanics in that. And let me just quickly tell you what it is. I will not go through all details. So the setting is the following. So what you have is you have a random walker that is random walking, and then once in a while it is resetting. So what is the framework? So you may think of this random walker, it is like a Brownian particle. If you go to continuous space and continuous time, it's a unbiased random walker, but more generally you can think of Brownian motion in presence of an external field. And well, if you want to get back to the situation that I was talking about, you just put the external field equal to 0. Okay. So you have an overdamped Brownian particle. So forget about if you know what a Brownian particle is, but it's basically random walker which is moving in a force field, and your evolution is taking place in discrete time. And what is the evolution? So there are two ways in which you can evolve. One is, so this is your location at the time instant I. So that's your previous location plus this is the diffusion. This is the random walker contribution. Okay. So this is a stochastic noise, which is which is a Gaussian white noise. So this is where the information comes in that given my current location at the next step, I have some probability to go here or some probability to go to the to like another point. So that's the random walker part, and that happens with some probability 1 minus r delta t. Okay. So r is a parameter that if you set r equal to 0, then you have just pure random walk. Okay. If you set r equal to 0, you have just this thing happening. While what is the second thing? The second thing is that, so given your current location, your next location would be one which is allowed by random walk, or it could be just your initial location. So these are the two possibilities. Xi is either your previous location plus some term or your initial location x0, and this will happen with the complementary probability r delta t, right? And you see that if you put r equal to 0, then you have just a pure random walk, Brownian motion. Okay? And this r, it is a parameter that is telling you, given you are at location x, what is the probability that you reset or you don't reset, which is 1 minus r. And for generality, we to be very general, we made it as a function of the space. It could be that you reset depending on where you are. Of course, you will always reset to the same location, but you may say that, well, I will reset with lesser probability if I am very far away. I will reset with a higher probability if I am close to my resetting location. So it gives you another knob, like you want to make a general theory. I mean, as general as you can make it to be, yet not compromising on the the realistic part of it. And eta, this is just a Gaussian white noise. This is just taking care of the fact that you have some probability to move to the left and move to the right. It is just a generalization of that. And these are the different scenarios that one can think of. So these pictures were drawn by Edgar. So this is quite nice. So you may have, you see this formalism, it can be generalized to 1, 2, 3, whatever dimension you are interested in. So this r is the resetting probability, right? So this resetting probability, it depends on where you are. So that's why you see a color coding. Okay. And what is the resetting happening? That this guy is doing random walk and once in a while it is resetting. So here the particle motion is not taking place in presence of a potential, while here the particle motion is taking place in presence of a potential, and on top of that you have resetting. Okay. So these are the general situations that you can think of. And what is this? I will give you only a brief idea of how do you do this path integral. So the idea is the following. Suppose you ask the following question, that what is the probability of getting trajectories that start at location x0 and end at x at time t without undergoing any reset. You may ask, you start from your initial location at your initial instant, what is the probability that I end up at this location at a later time without undergoing any reset in between? Okay, this is a valid question. We will see why it has important bearings on this analytical formulation. So, I have written those equations down once more. I mean, this is your previous location, which is previous location plus something leads you to your new location, or your new location is just your initial position with the corresponding probability, and this is the distribution of this noise, the coin tossing half. So, that is like 2 delta peak, and if you smoothen it out, you have just some Gaussian distribution. So, then see, this is quite like easy to write down. I ask what is the probability of a given trajectory that starts at x0, that goes through all these locations and end at x at time t without undergoing any reset. So, I have given you the points through which the trajectories have passed through, and I have told you that at each of those points, at each of those instants, no resetting has taken place. I start here, I end there, I go through all these given points, and I ask what is the probability that I generate this without undergoing any reset. And that is quite easy to write down. So, how do I do it? So, how do I go from x0 to x1? I have told you that the path has to go through these points. Okay? I have told you that the path at time 1 has to go through this one, time 2 go through this one and so on. And I have told you that no reset has happened here, and so on. So, how do I go from x0 to x1? I go from x0 to x1 by random walking, right, by diffusing, because I have told you that no resetting has taken place. That means, I have to, if I look at this equation, the first equation, I have to find a stick of the right length, a noise of the right length that would take me from x0 to x1. Okay, and that length is what? That length is just eta 1. Okay, so that length is x1 minus x0 will be what? It's just delta t times mu f x0 plus eta 0. Okay, and I know how the etas are distributed. So, what I have to do is, if I have to do it on a computer, I have to move from this point to that point, means I have to generate a random number of the right length that would take me from this to that, because I have told you that no resetting is allowed. And since it is a Gaussian distribution, I stick in that factor.
Yeah. This is purely classical.
This is purely classical. There is no.
So if you were assigning the x1, x2, x3, then you have to ensure, because if it's a classical trajectory, then the classical trajectory is nothing but a set of points that are mutually connected by canonical transformations. So all the points of the trajectory have to be related to each other by canonical transformation.
Well, this is the
case, if it's a random motion, it's evolving by itself. So it has to also basically that is what the classical trajectory is, that the action has to be an extremum.
No, so here I will come to the action. So here you have to remember, this is an overdamped Brownian motion. This is not really the dynamics is not governed by a Hamiltonian. This is an open system. No, you have noise coming in. So this x is really just superposition.
You are specifying it from before.
Yeah, this is not a Hamiltonian dynamics, because this is stochastic dynamics. So this is Hamiltonian plus something.
Let it be stochastic, because it's a classic. Since you are saying it's a classical. In the case of a classical trajectory, if the particle by itself can go, then so you have to give all the points.
I have to give all the points.
So how do you decide how many points you have?
No. I am asking. I give you these points, you construct a trajectory that pass through all these points. I will come to action, this action will show up in a minute. So, I think this much is clear, that given these points and given that no resetting has taken place, how do I construct this? I have to just find the random number of the right length, right, and then I just connect them and I get to from this to that. And so, how do I get the random number of the right length? Well, I know what is x1 minus x0, that is just delta t times mu f x0 plus eta 1. Okay. I know how eta 1 is distributed, that is distributed as this way. So, instead of eta 1, I put x1 minus x0 plus delta t fx0. So, that is how I get this factor. Because these etas are distributed as independent and identically distributed Gaussian numbers. So, I have to just connect them, and I have to ensure that at each of these instances I am not resetting. Okay? So, that is ensured by giving this factor. Okay? So, at each of the intermediate points, you look at I goes from 1 to n. So, at each of the intermediate points I am not resetting, and secondly I am sampling the right etas such that I go from x0 to x1 to x2 to x3 and so on. And then you can, so there will be a Jacobian of transformation and so on, but then, so this gives you a probability to go, probability of a trajectory that goes from one point to another without undergoing any reset in between, and going through a set of given points. But now you may ask, what is the probability that I go from here to there without caring about which intermediate points it went through, only condition it did not ever reset. So, what you have to do is you have to take this expression and you have to integrate over all possible values of the intermediate x's, and this is what you get, right. So, you integrate over all possible like intermediate values, and if you do that and you get to the right limit, you get to continuous time, because ultimately I get to continuous time and continuous space. So, you see that this has really the form of an action, this is the P no reset. What is the probability that I go from this point at time 0 to that point at time t without undergoing any reset. So, that means I have to integrate over all possible trajectories with the endpoints fixed, and the action is just this classical action. Okay. And now what you can do is that once you have this one, then you can invoke the path integral approach. Path integral approach what tells you is that this thing, this probability of getting trajectories that go from this point to that point without undergoing any reset in between, that is nothing but a propagator, a quantum propagator that takes you from x0 at time 0 to x at minus it. Why minus it? Because it is quantum propagation in imaginary time. Okay? There is no Hermitian, there is no Hamiltonian. So, the whatever Hamiltonian that comes in, it comes in through here. And so, like everything boils down to solving the corresponding quantum Hamiltonian. If you know the quantum Hamiltonian, basically you need to know the eigenvalues. The lowest eigenvalue will give you the steady state, because the lowest eigenvalue will be the one that is if it is 0, then that is going to give you the steady state. It will not show any decay in time. Maybe I show you this thing. Okay, there is a renewal theory approach that is also an important ingredient, but probably I skip this part. It turns out that you can do all these things exactly. You have to go to Laplace space and so on. It turns out that you can solve everything exactly, just building on the fact that since you know how these individual etas, the randomness at individual step, you know how they are distributed, you can construct trajectories that do not reset in a given time, and from there you can construct trajectories that do reset in a given time going from one point to another, and everything is kind of just, you have to be patient and work through, but the basic ingredient is this mapping to a quantum mechanical Hamiltonian. It turns out that you may wonder, well, it is all for one particle. What happens if you have many particles which are interacting with one another? Okay, and then probably the Hamiltonian is too difficult, and how do you go about doing it? Well, it turns out that here also you can do a lot of things analytically. So, here what is the setting that you have? Instead of a single particle which is coming back to its initial location, one thing that you may think of is you have an interface. For example, so this is not quite an interface. Do I have a piece of paper? Probably no, somewhere. Oh, here. Okay. So, I was looking in the wrong direction. So, this is like an interface which is fluctuating this way. Okay. So, you may think of the interface between oil and water. Okay, that is an interface. So, it is fluctuating, it is getting rougher and rougher, but once in a while it is becoming flat. Okay, you start from flat, it became rougher and rougher, but once in a while you are resetting. Okay, you may think of such a scenario. Well, we came about, this thing came to our mind because of some, when you consider a cancerous cell, if you look at the boundary of that cell, in the cancerous tumor, so that's described by something known as an Eden model, in 2 dimension, and that gets rougher and rougher. But once in a while, if you apply some chemicals like chemotherapy, you do undergo chemotherapy or something, so what you do is that you suddenly squeeze those or get rid of those fluctuations, squeeze the size to a smaller one. That's why one does chemotherapy. So this is this kind of setting. Don't take it too seriously, okay? So it's not that I have been able to solve the problem of cancer, but you can, so it's an interacting particle system, because an interface is composed of many particles, and they are bonded to one another by some force or and you can derive exact results for what are known as Edwards Wilkinson and Kardar-Parisi-Zhang. These are the 2 universality classes of interface dynamics, and you get kind of similar result, that if alpha is smaller than 1, you don't have steady state, where alpha is larger than 1. So let's come to the conclusion. So what did I talk about? So I talked about this general framework of stochastic resetting. So it's an analytically tractable framework to study a class of, these processes. They are known as, so Luca, this is Howard, no? What's the name of that guy? Your chairman, this piecewise deterministic guy. The Hogan, okay, so yeah, that's right. So these are processes which are piecewise stochastic. Piecewise stochastic, why? Because a fully stochastic dynamics is this one, but our dynamics is piecewise stochastic, that it's stochastic, but then this is deterministic. So there's a certain cut, you cannot define the derivative here. Okay, then you have this and then this. So this is a piecewise stochastic, what is known in the field of differential equations, stochastic differential equations, as piecewise stochastic process, and we saw that it leads to very interesting and novel time dependent or time independent steady state, and like a whole lot of things can be done analytically by mapping everything to this quantum mechanical problem, which, come to think of it, it should somehow like evoke some you should be surprised that how come this can be, or maybe you are not surprised, I don't know. So, and it can be generalized to interacting particle systems, and I did not have time to talk about animal foraging and home range models. This is the thing that I did with Luca. So there, this home range is basically, there are these animals, well, they move around searching for food or prey, but then at some point, during their exploration, they decide to come back. Well, they don't come back at one go, but then once they decide to come back, they come back deterministically, right? When they are when they don't know where to look for, then they do kind of random walk. They do like this, but once they decide, okay, now it's getting late, I have to get back, and then you don't do random walk, then that's not what you. So this is really a resetting in that sense. So
fire ant problem or desert ant problem, like they search for food, and once they get the food,
they come back. Okay, so they directly come. So these are the references, and thank you for your attention. So I hope I answered your question. It all matters whether the mean is finite. If the mean is finite, you are bound to get to a steady state. If the mean is not finite, you will not get to a steady state, although there will be some signatures of resetting. You will have a cusp singularity and so on, but it will. Sorry? If the mean is not finite, then it is not guaranteed that there is a time scale after which the particle will come back. So it will just keep on spreading. But still have a cusp, because that one point is very special. Something is happening at that point which is not happening at other points. So, yeah. Now you may generalize it to the situation that also people have done. So you may generalize it to a situation where you don't always reset to the same point, but you reset to a point chosen from a distribution. Each time you decide, okay, I'll reset to this point, I'll reset to, and that also can be solved to a large extent using the techniques here.
So resetting to alpha x, so that in the x you started this, and at a given time, right, so there is alpha t. So x is alpha t, there is a graph.
Huh.
So you reset only to that
No, so what is it that
So instead of you are resetting to a line x equal to 0.
huh, huh.
So instead of x equal to 0,
Oh,
x equal to
you
0,
move
there is another
okay,
line.
depending on the time that you are.
You set to different, right? But
Did you do this one? No. So that was, I think so. No, this I think people have not looked at. What people have looked at is you reset to a point that depends on your history. Like if you had reset to some points more often in the past, then you continue to reset to those points in the.
or resetting to also, this is one. The other one is that these stock fluctuations or something. So things reduce,
Huh.
or even in the population, if they reduce by the fraction of what existing one.
Huh.
Like it's 90% reduction or 30% reduction. So it depends on the value. It's not 0. Let's say 1000 to 30% down, which means 700.
Huh.
But if it is 70, then it is 30% down is whatever. But it is
Okay, so you just do some fraction of your, not really a real value, but some fraction of. Yeah.
some reduction.
The beginning you had two examples, and then in the test you ended the slides also with an example of homecoming.
Huh.
But the resetting is okay, but the fluctuations are very different and uncorrelated. For stock market, we can have some kind of relation with fluctuation and falling, but the population, which is used data, I don't think there's any connection with the fluctuations like
No, there is no connection.
for the deaths of people, right? So
No, I think the why I brought about those things, because this is to show that in those dynamics there are these, you have the same time scale over which there are two competing things happening, huge fluctuation and small fluctuation. It may so happen that the fluctuations at this instant are correlated to ones at the next instant and so on, but that's a second level of description. So this is the, I mean if you invoke correlation in this setting, then things become very difficult to compute analytically. Yeah, but
not the fluctuations part at all.
no, this one can look at, for example, the temporal correlation and so on. But so here mostly we are interested in the long time steady state, whether it gets to the steady state, like one time answer that you take a snapshot. But one may look at, you see this connection to path integral that breaks down as soon as you have correlation. Here what is saving you is that at every instant you are drawing you are tossing a coin, but the coin, the result that I am getting now has nothing to do with. So that makes it quite easy to construct those trajectories. Otherwise you have to be, it becomes.
Fluctuation, the hugeness alone is not the important thing. Also, there's a targeted effect.
Sorry?
The hugeness alone is not the thing.
No, not hugeness. The thing is that you have two competing ones. I mean, one that is going to generate small fluctuations. There is a particular scale of fluctuation. There is another one which is at a different level. It is huge in the sense that. Sorry, it has a goal also. So that there are possibilities of huge fluctuations. I mean, at the random walk level, there is no possibility of. So it may so happen that although you are allowing for the possibility of huge fluctuations to take place, you eventually don't see it in steady state. But that's the nature of the steady state. That the dynamic somehow managed to organize itself in such a way that in the steady state you don't see this, the second moment became finite and so on. But that possibility is definitely there. So in like in probability theory, like you have to keep all the possibilities. It may so happen that some are subdominant, some are like more dominant and so on. So that shows up in the form of the distribution. So Edgar, like, are you still there? Or did
Yeah, I'm here. Yeah.
Oh, okay. So please tell me, are there questions?
Yeah.
Or,
Yeah, I have.
Thank
It's maybe a curiosity, because you said that you have exponential resetting times, then the distribution is exponential, and the same with power law. When you have power law resetting time, you have power law stationary distribution.
Yeah.
So how general is this? If you take any other resetting time distribution, you will get also the same distribution in
Yeah, you
space
will
or-
get it because you see, if you remember this renewal theory, so basically you have to convolute your free propagator with the distribution. You see,
Okay.
and therefore this convolution brings in this feature. You remember that you have to ask, when did we last reset?
Yeah, I remember, but I wasn't sure that this convolution keeps the same functional form.
It is
as
more or less the case. I mean, the cases that I have checked, I don't know if there is a general theorem that proves it, but I have checked that for cases that I have checked, it is always the situation.
Okay, very interesting.
Oh, gamma function probably, I don't know. So I checked normal.
Because, right, so consider that exponential and power,
Huh.
they are usual asymptotes.
Huh,
The general asymptotes are either it is x to the power n or
huh,
x to the power
huh,
x.
huh.
So, right, these are the general asymptotes. So, this asymptotic thing is reproduced. But if you take arbitrary function, let us say gamma function, if it goes like that, so
That may not,
directly
okay.
go, you might get exponential
Okay.
at the end, or maybe.
Hmm.
Exponential.
But some features will be there. Some features, yeah, it may not lead to a gamma function, but some features will be there. It may not be so clear as a power law. and
Gamma function has a exponential decay. So, your distribution, whatever final you get, will have
exponential decay. So some will be there.
Yeah,
Yeah.
to some extent, I mean, because you're just thinking Laplace,
Huh.
you have the product of these two
Exactly,
functions in
exactly.
space,
Yes.
another function in space at different moment
Yeah.
in time. So,
Hmm.
so therefore, in space, those features are there.
Yeah.
So
Yeah.
it's a product of
Yeah.
the two.
Yeah.
So
So
whichever,
convolution, so it becomes a product of
whichever is shallower,
huh,
dominant.
dominant. Okay. Yeah. More questions or now it's
No, that was my question. Yeah, it's
Huh.
very good.
huh. Yeah, you have some questions or
No, I don't have more
okay,
questions.
okay. So okay, thank you very much. And thanks to everyone for coming, and especially thanks to Edgar for agreeing to give the talk in such a short notice, and that too on Skype, on Zoom. I mean, I understand it doesn't give you the required level of comfort, no, that one gets in, walking around and so on, but it's okay. And also to all the other speakers like Luca and Chandrasekhar and PK for, okay, thank you. Thank you. So Edgar, I talk to you later then, okay? So